I never noticed that before. That's one impressive link that Zoom provides. Interesting. Looks like can get started. Welcome back, everyone. I think I was spacing out, usually trying to start right at the minute. I was just noticing also that our Zoom controls are kind of at like its maximum to show most participants. This is kind of weird. For folks who are coming in through Zoom and can't quite see, this is what my screen looks like. This is going to be my letter to the ISU administration that we need some better technology. I'm running out the actual vertical space to show all the participants. I have just a little bit more real estate down here to show the whole list. So that's kind of impressive in a way. But in either case, welcome back, everyone. Today's class, we're going through section 7.2, which is actually kind of fun. This one is really just another look at U substitution with an emphasis on trigonometric integrals. So we're reviewing trigonometry as we go. Section 7.3 is, well, it's a type of U substitution, but it's its own special sort of substitution. This is a good section to take a look at before class because I feel like this one really jumps in the abstractness. The problems feel a lot longer. This is a good one to do a little pre-reading to make class feel a little bit more meaningful, have things make more sense. But we're going to continue on starting in example 2, just integrating as we go. We're taking our time on week 1 and week 2 because, again, it's kind of a review weeks that we're getting through. I'd say once we get past section 7.3, we'd be going in a little bit more than the normal pace of the course. But any last questions at all, folks, before we get started with today's work? Okay, well, the reminder is that section 7.1 is going to be due tomorrow. And as far as the due dates go in this course is that it's always going to be exactly a 1 week turnaround. So if we don't finish section 7.2 on Thursday, we'll adjust the due date. If we do somehow finish a due date early, usually in that case is when I probably would leave the due date stand since it feels like I'm moving up things that might be in your schedule. So at worst, pretty much all we're going to do is move the due date an extra day or two if we need that time. But here's where we left off in section 7.2. In section 7.2, we had what looks really kind of overwhelming, a huge overall arcing strategy for integrating a power of sine multiplying a power of cosine. But really only boils down to the parts that are highlighted. And let's say a little bit more about this before we jump into the problems. What our author strategy is indicating is look for an odd power of cosine. If you find a power on cosine is odd, then your substitution should just be u equals sine x. I guess I don't want to add too many errors to here. This will turn into a spaghetti mess. The other big takeaway is if the power of sine is odd, use cosine x. So you're looking for odd powers. Over here, both powers are odd. Well, excuse me, this power was odd on cosine, even on cos, I'm getting troubles with my evens and odds. Even on sine, we found an odd power on cosine, which suggests take the opposite function, equals sine x. So in other words, if you're looking for odds, pick the opposite function. On our next problem, that's exactly what we have here, an odd on power of sine. So we should pick cosine as our u substitution to make this all work. But then we're going to run into some problems because there is no odd power on this one, so we need a whole new set of identities to work this one through. Part C is where the reduction identities come into play. So if you don't have an odd power of either sine or cosine, that's okay. These reduction formulas are going to get you to where you need to be to integrate still in those cases. So let's give these all a try. Starting with this one right here. Well, it's kind of a mess. We have issues with the chain rule possibly being applied here and there when we go to use the U substitution. Our strategy says since the power on sine is 5 odd, use the opposite function, cosine. So u should be equal to cosine x. One related problem that can come up, I think this comes up in the homework as well, is what to do if they're both odd. Say this is power 5, power 11. If they're both odd, that means any substitution here is going to work, either sine or cosine, but you're making your work much more reduced if you pick the higher power, if they're both odd. So that will just mean you're doing less work algebraically. But here, if u is cosine x, then we can now write down, well, we can't really go with cosine x. What would be a better thing to put in here? Anyone spot the error? Exactly, the input is not x, it's t. We should go with cosine negative 3t to start this problem out. So that's the actual cosine function we have in the problem. Then next, the differential du.
Do we not take the power first, the power 6 for the cosine?
Yeah, actually, we go to just the power 1 on these. So we're going to call this whole cosine power 6 of negative 3t just u power 6 and go down the line. Occasionally, sometimes that would work, but if you went with power 6, du is going to involve 6 times cosine power 5 times the sine of negative 3t times the negative 3. So we would have a bigger thing that would emerge down here in the differential. So it's a little bit hit or miss with higher powers. That's why we usually go for just cosine to power 1. Next, the differential of all this is going to be negative sine of its input multiplied by the derivative of the input. In both cases, it's negative 3t. So here we're just using the chain rule to differentiate. Du is now equal to 3 sine negative 3t, where those negatives cancel from this derivative here, giving us just a negative 3. Now, this is not integration by parts, so for u substitution, we usually take this 3 here, move it out front to a 1/3 du equals sine negative 3t, and another omission here is we do need the dt for a full-on differential. Sorry for those weird omissions. So we're just about all set. The next strategy on the left is really just organization. Lots and lots of mathematics is really just organize a problem so your substitutions can get through in a reasonable way. So here's how we can organize ours. With what we've got so far, we have to give up one factor of sine. So where it says sine power 5, let's drop this down to sine power 4, negative 3t. We're okay with cosine power 6 because that's just going to turn into u power 6. So we copy this down. Then to the right of the multiplication, you don't need the multiplication symbol, but this is me organizing the integrand. Because we dropped the power by 1, we have to include it over here. Sine negative 3t. Now this component and this factor makes up the power 5 here. So we didn't break anything in algebra. Last thing we'll put in is the dt. And analyze everything we've got so far. So sine negative 3t dt is this portion right here. We're going to replace all of this with just 1/3 du on the next step. Let me use a pen that looks a little bit more reasonable. So this portion is 1/3 du. This portion is even better. This just turns into u power 6. So if we can find out what to do with sine power 4 negative 3t, our work is done. So here's where we're going to use some trigonometric identities to make this all happen. In fact, if you scroll up back to where the strategy was, the identities are already provided, cosine squared and for sine squared. But instead of trying to remember two different identities, go for the overall major identity for trigonometry. Trigonometry just begins with this equation, cosine squared I'll write it this way of x, so it's just a generic formula, plus sine squared x equals 1. So if this is the overall thing you're working with, but you want to maneuver something with sine power 4, the identity would turn into this. Sine squared x is 1 minus cosine squared x. So that's the identity that serves our purpose, dealing with sine power 4. So let's actually work with that now. Sine power 4 of negative 3t, first, doesn't feel like it even fits into this identity at all, but you can force it to work. Anyone know how to just make it work one way or another? Exactly, sine power 4 is just something squared again. So we rewrite this as sine squared negative 3t squared. And this is the reason why if the power of sine is odd, we had to pick a cosine. It's because the differential gives us one extra factor of sine, which takes something that was odd, makes it even. In other words, this identity by the red dot only works if you have an even power of sine. If it's odd, we're kind of stuck and our problem is harder by that substitution. So this then turns into 1 minus cosine squared of negative 3t squared. But that's great as well, because the moment cosine squared comes up from this right here, that's just a u squared now. So we have 1 minus u squared by that substitution. If we want, we can even expand that further and get 1 minus 2u squared plus u to the 4th power after filling out the line above. So we've got a paper trail now. The hardest thing about this problem right up here is just this mess. 1 minus 2u squared plus u power 4. You don't have to write this part down, but this is just for the sake of making the notes more readable. So once we have all that laid out, we throw in one overall big substitution. I made one small mistake for the way I like to format. I usually like to put a little extra space right here so that the 1/3 can go in front and we're not distracted by it on the next steps. Let's go down the line. For this portion right here, that's where the 1 minus 2 u squared plus u power 4 comes into play. Right here, we have u power 6. The last part in green turned into a 1/3 du. I'll throw the du here, and I often put the 1/3 in front. If you put 1/3 right here, that's all right. You might move it down in the next step, or you might not move it at all, and 1/3 is just to the far right in your answer. As long as it's algebraically correct, I'm not too worried about those stylistic choices. This is the point of celebration, and if this was a 10-point exam 1 problem, I would probably give a lot of credit to this step, maybe as much as 6, 7 points. If you ended your problem right here, you would probably only lose a few points, because this is the punchline to a lot of the sections in this book. Take something that we don't know how to handle in Calculus 1, by some magic, maybe it's integration by parts, a u substitution, you turn it into a Calculus 1 problem, and now it's just the formality. Distribute, find the ordinary antiderivatives, and we're on our way. So this is where we breathe a sigh of relief, in other words, when we get to this step. Any questions at all, folks, getting to this location? Okay, writing it all through, we have a third. Integrate. Let's distribute u power 6 inside. We can't integrate before we undo this multiplication of functions. So we'll have u power 6 minus 2 u power of 8 plus u power 10 du. Again, it's kind of relaxing at this stage. Now we're just using the power rule in reverse. So this would turn into 1/7 u power 7. Just a quick review on that if it's been a little while. When we integrate something like this, the exponent increases in size by 1, and then we divide by whatever the new exponent happens to be. So do it again. This one turns into power 9. So this is now all together minus 2 ninths u power 9. Finally, plus 1 11 u power of 11. And because it's an indefinite integral, we need our arbitrary constant of integration c. And just a quick border here. So we have our computations and substitutions on the right and our main work summarized on the left. Well, if you left your answer in this form, you still wouldn't have the full credit here. You might lose 1, potentially 2 points, because like we discussed before, we still have to undo our substitutions. A lot of times I think I've seen people do this where they know the antiderivative is going to look like that, and you know your substitution was this. If you just wrote cosine power 7 of negative 3t right there, that's an acceptable shortcut to make. It makes the notes kind of unreadable though, so I always show that extra step. So our last statement is to say we have a third times a 7. In place of u, it's cosine negative 3t to the 7th power. And that's kind of hard to format that way. Let me try again. Cosine power 7, negative 3t minus 2/9. Takes a little bit to just write this in. Cosine power 9 of negative 3t plus 1/11 cosine power of 11, negative 3t close the bracket, add the constant, and now we've got it, folks. Let me just move that partition over. This is finally our full answer. Loads of things you might do to this. Some people might distribute a third in. Other folks might take the greatest common factor out. I'm not too concerned about those small algebraic steps unless they serve some larger purpose. For example, if we had more to do with this problem, definitely simplify it as much as possible to make our lives easier. But if all we're doing is integrating and there's no terms that cancel, then this is an acceptable format of your answer. Any last questions or comments? Not at all. Yeah, I think this would be a great answer. And just to emphasize that statement, let's write another line to say, I think a lot of people would want to distribute the third in. That's just your stylistic choice for expressing your answer. Others would factor, like we mentioned. Let's go with the distribution. So equally valid is a 21th cosine 7, negative 3t minus 2/27 cosine power 9 of negative 3t plus 1/33 cosine power 11 negative 3t plus a constant. And when I write down the solutions to our homework sets, I'm writing down my own solutions where I felt like that was a natural stopping point for me. You can compare in the back of the actual textbook. Sometimes the answers look a little bit different. And maybe your answer is different from what's back in the book, different from what I wrote down as a solution. And if you're not sure if it's right, just send it to me. And I'll let you know if you have an algebraic equivalent form or not. But the emphasis on writing this out twice was just to say both are great answers. Other comments so far? Okay. For folks who've taken lots of trigonometry, another thing you might have said is there's actually a subtle simplification here. Cosine is an even function, meaning those negatives can be full on just deleted, removed. Let's do that. And it's still a great equivalent answer. I think this one is improved because we really dropped down the complexity by removing an extraneous negative sign we didn't need. The property is that cosine, negative theta, is just cosine theta, since cosine is an even function. But again, if you didn't pay attention to that, that's sort of tangent to what we're trying to do, where our thrust is mainly the calculus. And this is just a fringe identity in trigonometry. If you didn't see it, no harm if you left it in that form. Well, that's one problem of the day done so far. We have several more to get through, but any questions so far? Okay, let's try this out again down below. This looks like it's the nasty one. We have two even factors of sine, an even factor of sine and an even factor of cosine. This tells us essentially that u substitution isn't even going to be effective in this problem. Let's write this down as a comment. Both powers are even. And so u substitution, I'll often abbreviate as u sub, is not effective. I'm not saying it won't work. I'm saying you might need a lot of ingenuity to force it to work. So we're going for something that's going to feel more natural to make this happen. So let's say in this situation, use the reduction identities. And this is pretty well named, the reduction identities, because the purpose of them is to take these powers and literally reduce them. They're going to be divided by 2 each time we use a reduction identity. So the start of this problem is really just a bit of algebra. Let's begin with sine squared x times cosine squared x. Let's write those identities down on the right. Sine squared of theta, if we decide to use theta in our identity, is equal to 1/2 1 minus cosine 2 theta. So the feature with this identity is the power is divided by 2, but the input, the angle, is doubled when we go to use this reduction identity. And the next one for cosine squared, I like these because they are highly similar. It really helps the brain to memorize these. 1 plus cosine 2 theta. Only difference between these two identities is the sign in the middle. So memorize one, know the trick to get to the other, and this is a great way to absorb that information. Coming down over here, let's apply those identities to write out first for sine squared. That one is 1/2 1 minus cosine of 2x. Let me write this with not too many parentheses, just for the sake of making it readable. So that's a sine squared portion. Do it again for cosine, and we have 1/2 1 plus cosine 2x. That doesn't look like it's helpful, right? Because we're trying to integrate an ordinary sine squared cosine squared. It looks simple up here, except these are not easy antiderivatives. And now we've taken it down to this. It looks like a total mess. But we can simplify this down just by expanding. First, we'll take 1/2 times 1/2 to get the 1/4. That leaves, let's just write it out so the notes don't look mysterious. 1 minus cosine 2x times 1 plus cosine 2x. But now we're looking at a type of conjugate formula. In other words, if you take a plus b times a minus b, you get the difference of squares, a squared minus b squared. That's helpful just to remind ourselves that when we go to expand this, the expansion is actually pretty fast on this thing. It'll turn into 1/4 multiplying. It'll just be 1 minus cosine squared 2x. So that's the result of FOILing all this out. Reason being is when you go to multiply this times this, and that times that, the inner terms will just cancel off. That's why there is no middle term expressed in this way. Okay, so we are exchanging sine squared cosine squared. We're integrating this, 1/4 1 minus cosine squared 2x. We know the challenge of integrating this one is that right there is still a tough problem because the power is even, which is okay. We just use the reduction formulas again until we're left with odd powers of either sine or cosine that we're dealing with. So this is one of those problems that just keeps on going. So I guess let's keep on going. Any questions so far to this stage first, using the reduction formulas twice? Okay, well, let's use it a third time right here. I think the color coding this time is going to be really helpful. This is going to be 1/4 multiplying 1 minus. Apply the reduction identity again right here. So this is the line we're using. That means we'll get a 1/2, then a 1 plus cosine of something. Any volunteers for what should go here? Good call. The idea with the formula is whatever theta your input is, double it every time you use the identity. So if it was 2x, just double it again for a 4x. Which makes it tempting for us to call it a double eagle identity. I suggest not to. It's just the direction we're going, making it look like that. So from here to here, we do in fact double the angle, however. So now we've got a pretty big algebraic mess. This will integrate nicely for us. First, let me fix my parentheses here so it's readable. But we do want to expand everything out so it's more readily integrable. So first I'll distribute the 1/4 inside. We have a 4th minus an 8th, 1 plus cosine 4x. I guess we can distribute the 8th in next. So we have a 4th minus an 8th minus 1/8 cosine 4x. Here, a 4th minus an 8th gives us negative 1/8 minus 1/8 cosine 4x. Okay, so we did a whole bunch of pretty bizarre looking surgery to that integrand and ended up here. Yeah, question? This one in front or this one right here? Gotcha. That came from the distribution of this 1/4 multiplying that 1/2 in front. Honestly, it's pretty rough to visualize when you're looking at these parentheses, brackets, and so on. Other questions at the moment?
Yeah, shouldn't 1/4 minus 1/8 just be 1/8 instead of a negative 1/8?
Oh, because yeah, that'd be 2/4, or excuse me, 2/8 minus a 1/8. That's truly a positive 1/8. Thanks for spotting that. It's rough to do all this and just mess up the fraction arithmetic. Other questions at the moment? That space right there? No, that was more because of the big comment I wrote here. Wasn't thinking too much ahead. Yeah, gotcha. Well, let's finish off this one. And yeah, that's a lot of space coming down there. Let's just restate our objective now. We're integrating sine squared times cosine squared x dx. That is not an easy problem, but if you use the right identity 3 different times and then simplify the algebra just right, it means all you're doing is integrating that. So this conveys over to the antiderivative of 1/8 minus 1/8 cosine 4x dx. And the objective that we mentioned at the start of class of taking something really complicated, that's the left on the red dot, that you never do in Calculus 2, is exactly what we've done. This is now Calculus 1 integral. We can attack this in the normal kind of way. So this will turn into antiderivative here is 1/8 of x. Antiderivative here, it's a little bit tricky because of the 4x here, but if we follow our nose, we can find it pretty rapidly. An antiderivative of a negative cosine would be a negative sign. So I would go like this, negative, put in a bunch of space, sine 4x. We had an 1/8 already, which says we should divide that 1/8 by 4 and get a 1/32 times the sine 4x plus the constant. So that's one way to find the antiderivative. But this is really tricky thinking at first, going from here down to here. So let's look at it a second way. First, any questions at the moment? Okay, this is again one of those antiderivatives that we do so often. In the reading itself, our author often takes this shortcut right here, and it is a really big shortcut. So we should explain it a little bit more just to show how this one really is going. So that's our end answer on this problem. There's work all over the place. So I'll box this out just to emphasize, never a bad step to take. But if we're thinking about antiderivative of a 1/8 cosine 4x, let's look at this again. I'm excluding the negative sign just for the sake of simplicity on this one. So imagine we're not worried about that negative there. We're trying to hit a 1/32 sine 4x. So one thought here is you could just do a u substitution. U would be equal to 4x. That's the 4x right here. The differential du would be 4 dx. We do not have a 4 left alone as a factor inside the integrand, so we can divide it out. 1/4 du equals dx, and come back over here to write, it's now 1/8 antiderivative, let me write out this way, times 1/4 antiderivative of cosine u du. So that's what the u substitution would look like to this stage. Does that look right to folks so far? Okay, then this is the step where we get the 1/32, just multiplying an eighth times a fourth. It'll be sine u plus a constant, which means we get 1/32 sine 4x plus a constant. That's a lot of steps in a problem that's already big. So again, this is another cell on that shortcut because it's used quite often. So another way to look at this was, if you have a 4 right here, let me pick a better color. If you have a 4 right here, you're just taking this 1/8 and dividing 4 into that location to get the same exact result we saw down below. So we multiply by, almost got it, 1/4, whatever the coefficient should have been right here. And if that was a 1/4 instead of a 4, we would multiply it by 4. So these are always related by the reciprocal. So that's a really slick way to deal with the u substitution. In my class, I only ever take that shortcut if it's linear, like a 4x. All other u substitutions, I always show the full steps for because it's just good practice on those. But these come up often enough that this could save you hours in this course once you get the feel for this kind of shorthand or shortcut. Well, we did it, folks, and either way, the takeaway for this problem is watch out for these kinds of arrangements. It could just be integrate sine squared. We'll leave that reduction formula, or it could be cosine power 4, or a combination of both like we did right here. What I'm going to try to avoid is like sine power 4, cosine power 6, because the algebra just gets too out of hand for those larger kind of problems. And let's take a look at what we've got next. One last one. This one actually doesn't really fit the pattern because the problems that we were looking at were factors of sine to a power times cosine to a power. This is a cotangent, and so this is kind of the odd one out in the notes. Here we need a whole different strategy. And the sad thing about all of this is there is not a strategy for every combination of trigonometric functions being multiplied together. I mean, there's 6 trigonometric functions. They have wildly different properties. And so whenever you see something like this, it's not a sine and a cosine, it's essentially going to be a new ad hoc method for every new arrangement of trig functions inside here, unless it's a tangent and secant. These tend to go really well together, just like sines and cosines. But everything else is like its own problem where we just have to find our own strategy. But here's one great way to think about these. One strategy is just to reduce the integrand using trig identities. And sometimes the identities are not all that too involved. We just have to do some algebra and start reducing. So I'm going to begin by just ignoring the whole problem, focus on the integrand, cotangent cubed x times cosine squared x. The very first thing we need to know is, what is a cotangent? Do we put sine or cosine in the numerator for that one? Good call. That one's going to be a cosine mentioned in class. Since it's cotangent cubed, we have cosine cubed of x divided by sine cubed of x. One way to think about this is if it's a cofunction, the cofunction goes in the numerator. If it was tangent, then sine would go into the numerator. And it's multiplied by cosine squared x. Doesn't look like this was super helpful, right? Because it doesn't even look like we did much of a reduction. It looks maybe more complicated. we now have cosine to the power of 5x divided by sine cubed x. But this is actually a big improvement. We're back to just sines and cosines. Still a little bit different from the rest because sine is in the denominator. That essentially forces our hand on the substitution. Our substitution should just be whatever is in the denominator. Now we need to hope for the best. So here's our problem. We're going to integrate cotangent cubed x, cosine squared x, dx, but then that just boils down to, let me write it out this way, integrate cosine power 5x, divide by sine cubed x, dx. So let's go from there. This can happen in some of the homework problems where we just need some trig identity to get through it. If you feel like you're stuck, that identity is needed and you're just not sure, don't hesitate to write about it. I'll be happy to help out. But now we're in this position. This is the natural choice for a u substitution. You ought to pick u equals just an ordinary sine x. I mentioned the numerator is not going to work great for a u substitution. I'm going to sketch it out here just to explain why. It's equally important to know when a substitution fails versus when it succeeds. If we did try u equals cosine x, then the differential du is negative sine x dx. And sure, we have sine in the denominator, but that is not helpful to us. To use this differential, you need a factor of sine in the numerator. It's corrected by multiplying by sine over sine with a sine power 4 now in the denominator. That's getting excessively complicated. So in this situation, you really want your u to be the denominator. So going that more hopefully promising route, the differential du turns into this. It's now a cosine x dx, and that will work for us because we have factors of cosine available to us in the numerator. So again, watch out for these kinds of things. Just because cosine comes up, it's useless unless your factor of cosine is expressed in the numerator. Unless you had 1 over cosine x, then you might be in good shape. So we're back to the strategy of starting to separate things out because we give up one factor of cosine to the differential, leaving cosine power 4. So we've got cosine to the 4th power of x, divide by sine cubed of x, times cosine x, dx. So denominator is going to turn into our u cubed. Cosine x dx rather, is our du. All we need to figure out is what to do with that. We've seen that strategy before, though. It's the same as before. We take cosine power 4, factor this as cosine squared. So cosine squared x squared. We hit it with a trigonometric identity. Think cosine squared plus sine squared is 1. So if you isolate for cosine squared, you get 1 minus sine squared x squared. And you could just do your substitution right here and now as this problem sits, as 1 minus, where it says sine squared, we can throw in a u squared, squared. Oh, here just to show, that's where that substitution came from. Lastly, expand all this out and just toss it back into the integrand. So 1 minus u squared squared becomes 1 minus 2u squared plus u power 4. That almost feels like deja vu in a way. So this portion gets connected this way. And now our integrand is all ready to go. So again, if you see something that doesn't match any strategy that you read in the book, you saw in the notes, the problem is probably more along these lines. Just do something expressing everything in terms of sines and cosines could work. Try to involve an identity if it seems helpful. And then looks like we're on our way if everything works out just so. So let's see what we've got. In the numerator where we have cosine power 4 highlighted in yellow, it's 1 minus 2u squared plus u power 4. We're dividing that by u cubed. And lastly, where it says cosine x dx, through this substitution, we're just putting in du. That's not a bad problem to integrate, but as much things in calculus, you don't want to integrate it in this format. We need to rearrange this algebraically until we have several terms separated by pluses and minuses, integrate term by term. So here's the division step. We have 1 over u cubed minus 2u squared over u cubed plus u power 4 over u cubed du. Next step, let's actually do the reductions. For me personally, I never try to integrate in this format. I feel like the directionalities with whether you're increasing the power or decreasing the power is vague enough when you're integrating, and even worse if your base is in the denominator. In my opinion, it's more straightforward if you call that u power -3. This one, we do want a reduction, but here we want to reduce this in a totally different way. We want the power of u to stay in the denominator on this one, because 1 over u is a completely separate antiderivative we have to watch out for. Deserves a new color. So watch out for 1 over u. That turns into a natural logarithm in its antiderivative. But for every power of u, it's a good call to keep its base up in the numerator. Just not u power -1. That one's a logarithm out of nowhere. From here, we just have a u. And now it looks like we're mostly on our way. We're going to integrate term by term like we mentioned. We can't find the antiderivative of what's in yellow, divide by the antiderivative of what's in blue. Turns out those kind of things almost never work out. When they do, it's a usually very big coincidence. So last step, use the power rule several times. This becomes -1/2 u power -2. Again, the directionality is weird, but you're always adding 1 in the antiderivative. So this turns into a -2, for which we have to divide by that new power. This one is the one we're watching out for. This is -2 times the natural logarithm, absolute value of u. Even the absolute value is important, so don't forget those absolute values there. This extends the antiderivative into almost the total real number line. You still can't put 0 there, that's undefined. Then plus 1/2 u squared and a constant. One last thing we have to do is undo these substitutions and we're on our way. Any questions at all, folks, to our last step? Okay, lots of ways you could do this one. I'm going to write it out in what might seem natural. For me, if I saw this, I'd probably just go -1/2, put in a parenthesis because u is a sine x. And sure, we do write things like sine squared x, sine power 5x. But when the power is negative, it's probably not a good idea to put it here because it's easy to confuse that with the inverse function. So I'm just going to put the -2 here. For me, I'd probably just leave it in that format. But if you decide to make this a cosecant squared, that would be just fine. So the next one is going to be a -2, natural log absolute value, sine x, plus, oh, I'm running out of space here, 1/2. Here, because the power is 2, this one is okay to write as sine squared x. This one has really no chance of a miscommunication. But again, a -2 here is open to interpretation. That's debatable what exactly you meant. Last thing here is add a constant of integration. If you run out of space, just do the normal thing you would do in a notebook paper, drop a line and just keep on going. So it looks like we've got it, folks. Antiderivative of this pretty strange problem involves just some review work from trigonometry, then back to ordinary u substitution. Its major purpose is just a reminder that sometimes there is no strategy for these kinds of things. Sometimes, most of the times, they're all one new ad hoc method for every new problem you put on here. For example, if I change this to power 4, might go totally different. Might be a tremendously hard integral out of nowhere. But we did it, folks. That's the result on this one. We're going to change gears for the next problems and work with products of powers of tangent and secant, which go together really nicely. And we'll do one more that's kind of an odd one out. There's no formula in these notes that helps us with this one. But if you already have the idea in the back of your mind, good on you. This one is integration by parts, it turns out. So let's now pause here and look at a new strategy. So this time we're dealing with powers of tangent, powers of secant. The old strategy was to look for odd powers and pick u to be the opposite function, but it does change up on this one. It says, if you're looking at powers of secant and spot an even power, you should use this substitution, tangent. The reason for that is, well, the derivative of tangent gives us secant squared. So the game on even and odd powers changes on this one suddenly out of nowhere. The next thing we're looking for is, if you find odd powers of tangent, your substitution should be the opposite thing, a secant. And sometimes either one of them could work. You could have secant being even, that's this problem, tangent being odd, like in this problem, which tells you either substitution here is going to work. That's kind of exciting because that means your answer could look spectacularly different from my answer if you use a different substitution, but they are going to be algebraically equivalent through trigonometric identities. So if your answer looks really wild, that would be the reason why. You probably have the right answer. If you're not sure, you could always have me take a look at it. But let's give this a try. Secant power 4, tangent power 5. So like we mentioned, either substitution works. In this stage, if you want to work as efficiently as possible, which is a mathematical way of saying do the least amount of work, so you make the least amount of errors, pick the highest power if any substitution works. So I would automatically go for u as tangent power 5. Not because it's the only way to make it work, but it's the most straightforward approach now. Excuse me, I would make u be tangent x, so that we have u to the power 5 right in this location. Just as on the last set of problems, all of our substitutions are going to take tangent and secant to just power 1. But if that's our value for u, du is the derivative of tangent, which is now secant squared, x dx. If that was secant power 5, then we might be in a bit of a trouble with that. But this really works out because we're just going to give away 2 factors of secant. So here's a strategy where we're not really doing too much in the integrand except from just organizing it. Due to the secant squared right here, we factor secant power 4. It's now secant squared of x. Then hold that thought, we write in tangent power 5 of x. We try again, tangent power 5 of x. Then we come back to this thought, it's down to secant squared. So to maintain the all-important equality, we bring in secant power 2 now, and dx. Oh, thank you for that. It definitely looks like sine. I said secant, but wrote sine. That should be secant squared of x. Thanks for that. I must have done a micro sleep at that moment. So now the secant squared here, definitely looks odd because we had secant power 4, but that's its purpose. We now get a du in this location. In this location, we've got a u power 5. And you'll notice that there's definitely a process to almost every single one of these problems. For this one, we just need a trigonometric identity, and our author provides some. The secant squared identity, the tangent squared identity. But just like we mentioned from before, with trigonometry, there's 2 core identities you always want to think about. The one being cosine squared theta plus sine squared theta equals 1. The other identity is going to be tangent squared theta plus 1 is secant squared theta. And these other versions down below here are just the 2 different ways to say this same exact equation. Oftentimes, this identity is written in this way, however. Tangent squared plus 1 is secant squared. And then we just write it in whatever way that suits our purpose. We're trying to isolate secant squared, so we're usually using it in this format, in this situation. Secant squared of x is now tangent squared of x plus 1. That's great because this part right here becomes a u squared. plus 1. And now we have our last substitution we're going to make right here. And by the way, maybe one more comment on these identities that we're putting down. There's two major ones, like I mentioned. The cosine squared plus sine squared is 1. If you divide this whole thing by cosine squared, you really get this one. This is the next major identity. Turns out there's a third, though, but the third one is an easier one to get to. Take your tangent and go to cotangent. Square it like before, copy the plus 1. Take your secant and just go to the cofunction, cosecant. And that's the related identity coming off the one right above. So that's a great way to think about how to memorize these. There's a definite reason some of these functions are co to another. It's because you can sometimes write down equations in this kind of way. Memorize one, the cofunction gives you the other. But there again, they're also placed here. And at the end of the day, we just throw it all back into the same place. This problem is not too different than the first couple problems we've done on these notes. But any questions so far, folks, about any of the identities or substitutions before we put it together? Okay, so here's our big punchline to all of this. In place of secant squared x, follow these identities, and we have a u squared plus 1. Then multiply that by u power 5. And the whole secant squared x dx is just another way to say du now, per our original substitution. This one goes really fast because now we're just integrating u to the power 7 plus u to the power 5 du. Really not too much more to say on this one. Next step, we get 1/8 u power of 8 plus 1/6 u power 6 plus a constant. And then finally, we just go back to the original substitution, which was a tangent, and write it in. Our overall answer is now 1/8 tangent to the 8th power of x plus 1/6 tangent to the 6th power of x, then add our constant. So we've got it, folks. That's our antiderivative on this one. And I do have a homework problem where, again, it looks kind of like this. You could pick either identity. Your answer is either going to look like this, or it's going to involve like 4 or 5 terms if you went for the other identity. So it could look very, very different, but your answers are amazingly algebraically equivalent. They'll only differ by a constant. Any last questions at all, folks, on finalizing this one? Okay, so that's how secants and tangents work. Let's try this out again on the next one. Tangent squared from pi over 4 up to pi over 3. Part A looks like it's the harder problem. But in my opinion, this one's worse, and it's not just because of tangent squared being a foggy thing to integrate. It's because it's also a definite integral. We have to evaluate all of our trigonometric evaluations for these types of angles when that easy evaluations of an exact value is apparent. So that's what makes this problem a little bit harder. Let's see, let's drop it down a line. And do it down here. But really the first problem with this thing is tangent squared is not a great function to deal with. There's really no good u substitution at all for us to use on this one. We need a different identity or a different idea. Anyone have an idea or an identity that we could use on this one? Yeah, it's kind of mysterious when we look at this sort of thing. One thing we could try is, why doesn't u substitution work? I claimed it doesn't, so if we can convince ourselves of that, it actually helps. We think more about the problem. So if we try something, well, our strategies indicate pretty much you've got a tangent and secant to work with. U equals tangent x. The differential du equals secant squared x dx, but that's not too helpful for us. We don't have a secant squared here. Or do we? It just depends on how you write tangent squared. If we rewrite this, you could get a secant squared to come up, and maybe you don't even need this u substitution. The other thing that we could try is u equals secant x. This looks less promising because now the differential is secant x times tangent x dx. The only way to make this work out is come up here and multiply by secant over secant, so we can get a power of secant to appear. Doesn't look too approachable. So all that's left up to us is to try an identity. So let's say here, use a trig identity. And if you're doing this as a homework question, here's one thing that you could try. Just put the problem away for the moment, go to the trigonometric identities, and usually the first three are a pretty good call for something to try. If something like this came up that you really need, say, that specific double angle identity for cosine, I would probably bake that into the problem as a hint. You need that specific identity to make progress, especially if it was an exam problem. I'm not going to throw a random identity that we have to somehow discover on this list to make it work. So let's try out these first. Let's just throw it on the notes. So here's our trigonometric identities to try, the Pythagorean identities. Because tangent squared came up, we can try this one here. Doesn't seem like it's helpful at first, right? Because this one says tangent squared theta plus 1 equals secant squared theta. But keep in mind, this is three identities, and every one of these can be rewritten in three different ways in themselves. Could go up here and just rewrite tangent squared theta is therefore secant squared theta minus 1. That turns out to be the identity that actually works on this thing. So we can now say the integral from pi over 4 to pi over 3 of tangent squared x dx through this identity is going to just be the antiderivative from pi over 4 to pi over 3 of secant squared x minus 1. So there we've got our trigonometric identity pulled out. Next thing we need is an antiderivative. Anyone spot the antiderivative for the secant squared? Good call. The derivative of tangent is the secant squared. So that's its antiderivative right out of the gate, just a tangent x. I'll do this one. Antiderivative of negative 1 is negative x. And we have to evaluate this whole thing from pi over 4 to pi over 3. So that's our strategy on this one. Again, it seems really kind of odd that we can find an antiderivative for secant squared, but not so easy for tangent squared, unless you run it through this identity. Now it's a approachable problem. Next thing we're going to do in the definite integral is rewrite tangent pi over 3 minus pi over 3. That's using the upper limit of integration, so same song and dance with the lower limit. Tangent pi over 4 minus pi over 4. And here's the related comment that we do have to make here. We do have to evaluate all of our trig functions, whether they're on homework or exam settings. So we must evaluate giving exact values. So in other words, if we had, say, tangent 3, this is considered exact and simplified. But if you have tangent pi, we could evaluate this one. This is sine pi divided by cosine pi. Sine at pi is 0, cosine pi is negative 1. So this one evaluates to 0 exactly. So we have to do those evaluations on these trig functions. And it's something you probably were expected to do in Calculus 1. Major reason for this is I'm pretty sure the Calculus 3 teachers as well have this as an expectation. Trig comes up a lot in Calculus 3. You integrate on things called polar coordinates, cylindrical coordinates. Trigonometry is all over the place. So think of this as kind of a warm-up to that. if you feel rusty on evaluating these trigonometric things, then one thing you can do is throw down a unit circle diagram. Now, from the unit circle diagram, place down these angles that came up. We had a pi over 3. So that's this angle. And pi over 4 also came up. That's at the 45-degree line, so it comes out this way. The next thing you probably want are the coordinates at these points. At pi over 3, we have coordinates going down, 1/2, going left, root 3 over 2. And for pi over 4, just so that the diagram doesn't get too busy, I'll write the coordinates this way. It's root 2 over 2, comma, root 2 over 2. So the same x and y coordinate. That means when we go to evaluate these things, we can now say tangent pi over 3. We come up here to where the angle terminated on the unit circle. It's sine divided by cosine now. Sine is the y coordinate, root 3 over 2. Cosine is the x coordinate, 1/2. So this just reduces down to a root 3. And likewise, tangent pi over 4. This is going to be root 2 over 2 divided by root 2 over 2, which means it evaluates to exactly 1. Let's write it in just for the sake of connecting the thought. So with those values, we can come back over here and say, this becomes square root of 3 minus pi over 3 minus, over here we have a 1, minus pi over 4. Reduces just a little bit further. We now have root 3 minus pi over 3 minus 1 plus pi over 4. If you ended it here, no harm done, but I think most people would want to go for adding the fractions together. So we have root 3 minus 1, and now let's do something in the scratch. We have from pi over 4, that's 3 pi over 12, minus pi over 3, but that's minus 4 pi over 12. That's enough to tell us that those combine to negative pi 12ths. So we're going for the exact answer, but this was okay with me right here. If you did it on that step, I would understand. Fractions are not my favorite either. We did it, folks. The major takeaway with this problem is watch out for the identities. They show up a lot, but also is more about, we also have to evaluate these trigonometric functions when they come up. They won't come up a lot on exams, and if it does come up on exam, I do provide on the notes as a handout, last page on exam 1 and the rest of the exams, the first quadrant of the unit circle right here telling you all the x and y coordinates, just as a help for evaluating these functions. So you'll always be able to use that information there to do these kinds of evaluations as they come up. We did it, folks. This was kind of a nasty one. I think there's a similar one in the homework where it's like a cotangent squared as opposed to a tangent squared. But any questions on getting through this one? Okay, so this is at the weird part of the class where I have to remember we're at 4 minutes and some change left over. Oh, good call. Questions so far?
But an easy way to remember the first quadrant of the coordinates or the chart
Yeah, going this way.
is if you just take your 3 coordinates that you have for the 3 main sections of the first quadrant.
You mean like here, here, and here, that white space? Oh, gotcha.
If you take all of the coordinates, so your 3 coordinates that you have for each of those sections,
Sorry, just trying to get it in there. Pi over 4, and then pi over 6 would probably be in the mix.
if you have all of your coordinates, they're all over 2. And then you just write it, starting on the left-hand top, you just go 1, 2, 3 for the numerator, and then on the next one, it's just 1, 2, 3. So it's a real easy way to remember it. Just remember they're all over 2.
I like that, yeah.
And then 1, 2, 3.
I think it might be better to see that on a real diagram. Let me see if I can pull that up to connect that thought. So I want unit circle trig diagram with radians and coordinates. Sure, we've got some good stuff here.
So if you zoom in on the first column,
They showed me a good screenshot. Where'd it go? There it goes, there it goes. They lied at first, but they eventually told the truth once we got through the ads.
so in the first quadrant, if you look at all of them, every single coordinate is over two, so it's really easy to remember that. And
Okay.
then start
Yeah, good
on the
call.
left and the bottom right side, count again, 1, 2, 3, and then if it isn't a one, it's just a
Yeah, I like that. So what he's saying is you go for these values, 1, then √2, √3. If I say this right, and then on the other end, 1, √2, √3. Denominators are always 2 on these middle ones. And just remember, these are flipped. Was that the essence of what you were saying?
because all you have to do is the over two.
Gotcha. So if you didn't hear it quite well in Zoom, then he's mentioning all these fractions in the middle are always over 2. Count off the 1, 2, 3s, where it's a √1 reduced to 1, √2, √3, backwards on the other coordinate. Yeah, that's a great mnemonic for thinking about these. Thanks for mentioning that.
And then obviously.
Yeah, from here on out, you're just dealing with those issues. Absolutely. Just using the idea that, for example, if you're here, your cosine value's got to be that negative value going down below. But thanks for mentioning, yeah, that's a great way to memorize that kind of diagram. And this is what I provide on the real exam. Quadrant 1, I formatted it as a table. That way it's just available for anyone that's ready to go on that. But you might want to practice this a little bit going into exam 1. Just write down your own unit circle, fill in the radian measurements and the coordinates. And if you only fill in quadrant 1, then you can extrapolate through the entire unit circle, and you're really on your way on that. So I'll leave that on the notes just as a great way to think about doing these kind of problems. We'll have lots more opportunities to do these evaluations, but I think this is a good stopping point for us. We ended right when we're supposed to end. That's kind of rare in this class. We're usually going to be right around 8:37. Any last final questions before we call it a night? Okay, well, have a great night, folks. We have a weird class where we meet again on Thursday, but we'll just be finalizing these notes and starting 7.3. See you all tomorrow.
I've got a question about the homework.
Yeah, go ahead.
So I'm worried I might have got the wrong book because the page numbers don't line up. Would you, sorry, know like the first problem on the homework to see if it's the right book?
Yeah, and in fact, for every one of these assignments, if you click on the assignment itself,
Mm-hmm.
I've got the PDF typed out here, just so that in case you're using an older edition, you'll know what the actual problem should be.
Okay.
So you can pop out this PDF on every single assignment to double check.
Perfect. Okay. Thank you.
Yep, and one more thing, also on this PDF, if you scroll to the bottom, that's also the right answers to the odd questions as well from the most recent edition.
Oh, perfect. Alrighty.
Well, have a good one.
You too. Thank you. Bye.
Oh, no worries. Yeah, thanks. Yeah.
Yeah, I tried to remember them from like.
Yeah, it's rough. To be honest, each time they tell me to teach trigonometry, it feels like I'm just refreshing it all over again. It's gone with about 8 months. It's out of your head, it feels like, if you're not using it. It makes it tougher, yeah.
Like chicken is very, it's like easy, it's like, oh yeah, just.
Oh, yeah, yeah. Then we get to this, like, no, why is it free then?
Yeah, and not a very good one.